Hi, I'm Luke Houston.
Hi, I'm Grant Beaton.
Hi, I'm Ross Boyd.
Hi, I'm Sean McMorrow.
Hi, I'm Walker Graham, and we are Group D, tasked with the design and development of an airborne wind turbine.
Airborne wind is a relatively new sustainable energy source and is based upon the premise that at greater heights there are faster, more consistent wind speeds to be exploited. For the system, the flight of the kite in reel out generates electricity. The system converts the strong aerodynamic forces exerted on the kite into tension through the tether, which then spins a drum connected to the generator, producing electricity. To gain a better understanding of the system, modelling and simulation studies were carried out before practical work began. The aerodynamics of the kite play a huge role as this creates the tension, turning the drum and producing electricity. The kite was modelled first in 2D to understand the forces at work, and then 3D to derive values for lift and drag. Obtaining various lift and drag values allowed the optimal flight path and maximum power output to be calculated. For optimal output, the kite is flown on a figure of 8 path. This allows the kite to maximise the power available from the wind as it rises to its maximum tail length. This was simulated on MATLAB to help visualise the ideal path the operator should take. The next stage of simulations was the generator itself. By creating a Simulink model, the power output expected from a scaled down model could be predicted and used to verify our lab results. With the lift force acting on the kite being converted to tension to turn the generator, the group felt it was important to obtain real tension results at various wind speeds. This was done in the James Watt Wind Tunnel. While these tests were underway, generator and air control testing were conducted in the lab. The generator testing started small, with man return, then driven by a motor. After that, reel in and reel out motors were set up to more closely exhibit the real system's behaviour. With reel in and reel out phases both practically implemented, testing could be conducted to see the capabilities of our prototype. The distinct reel out phase is shown with a stepper motor acting as the kite, creating tension in the tether and turning the generator. The reel in phase then occurs when maximum tether length is reached, symbolising the kite being brought back to its starting position. The kite is always ruled out at 1/3 of the wind speed. For testing, a stepper motor was coded to implement this. The prototype would allow the user to dictate the wind speed the kite was experiencing, and the system would show the power output available. The kite control system was responsible for steering the kite during the reel out phase of operation. The user input controlled 2 servo motors within the control pod, varying the tension in the kite lines and enabling movement in all directions. An IMU was included within the control pod to measure the roll angle, displaying the kite flying conditions on a simple user interface. Bluetooth wireless communication underpinned the kite control as it allowed remote control of the motors in the air. Sufficient subsystem testing allowed for successful integration to take place, leading towards the physical assembly of control pod in 3D printed housing. With more time, the team would have liked to test the air control system and ground system together in either the wind tunnel or outdoors.